Welcome. Today's video is about number systems. You may have heard that computers work with information by representing it with ones and zeros, and that these ones and zeros are used because computers use transistors or small switches to either represent a value as being on or off. You may have also heard that computer scientists use other number systems such as octal and hexadecimal to represent long binary numbers to make it easier for them to work with. But what are these number systems and how do we use them? We're not going to be able to understand a computer and how it works at its most fundamental level until we have a good grasp on these number systems and how to convert between them. We're going to explore a very short history of them and how we got to using what we call a positional number system that we use today. We're going to have some terms like a radix or base, a grouping in place, weight, and range. We're then going to look at conversion between bases. Primarily, we're going to be talking about converting from decimal, the number system that we all know and use on a daily basis, to either binary, octal, or hex, or the reverse. We're going to look at how you take a binary number, an octal or a hexadecimal number, and convert it to decimal. Let's start by looking at some number systems that were used in the past. Here we have representations of the Egyptian and Roman numeral system. You'll notice here in the Egyptian number system that they use hieroglyphs to represent different values. A value of 1 was simply represented by a single stroke. A value of 10 was represented by a cattle hobble, this symbol here. So if I wanted to represent the value 11, I would use 1 cattle hobble and 1 single stroke. You can see in a more complex number down here, like 4,622, that we have 4 water lilies, each representing 1,000, 6 coils of rope, each representing 100, 2 cattle hobbles, and 2 single strokes, bringing us to our grand total. Roman numerals didn't change all that much. One difference was that you could preference a symbol with another to remove value from the symbol. So for example, a V in Roman numerals is a representation of the value 5. If I put a VI, I would have representation of 6, similar to what we saw here with the Egyptian hieroglyphs and a rope and a single stroke. However, if I put IV, I've actually reduced 1 from 5 and I'm representing 4. Other than that though, these two things are largely the same. What they lacked is an ability to represent the amount of symbols you were using here as a single value. A little bit later in history, a number of positional number systems emerged. The one we use today is called the Hindu-Arabic number system, and we have a representation of it here, and I'm sure it seems very familiar. This is obviously the number 1125. But what we're actually representing here is 4 different places. And these positions represent powers of the radix. The radix represents how many digits that we can store in any place or position as part of the number. So for example, in decimal, we can store up to 10 digits in one place. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. As soon as we go to 10, 10 is actually a 1 and a 0 that exist in the second and first places. Let's see how this is different now for different bases. A decimal or base 10 number is represented like so. In octal, however, we only have 8 numbers to work with before we go over to the next place. Here we can see we have 0, 1, 2, 3, 4, 5, 6, and 7. If we want to represent an 8 in octal, we actually represent that with a 1, 0. What we're denoting is that there's 1 in the 8ths place and 0 in the 1s place. Similar to decimal, where I would have 8 in the 1s place and nothing in the 10s place. In binary, we have even less digits. We have only a 0 and 1, which we know, of course, correlates to a computer's natural state having electricity either on or off. In binary, if I want to represent the number 2, since I only have a 0 and a 1, I actually represent a 2 with that same 1, 0. The 1 is in the 2's place and the 0 is in the 1's place. Hexadecimal is interesting because we have to represent more than 10 digits. So we have the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. but then we have still 6 more digits that we have to represent. How are we going to do that? The answer is with letters. We use A, B, C, D, E, and F to represent 10, 11, 12, 13, 14, and 15. So if you're representing the number 13, you represent that with just the letter D, or I should say the digit D. So now that we've talked about different radixes or bases, meaning decimal, octal, hexadecimal, and binary, what do you think the base was for the Roman numeral system? Let me know in the comments down below. So why do we use decimal? There's actually any number of options that we could use for a base in a positional number system. Quite simply, we believe it was because we like to count on our fingers. Interestingly, the Aztecs actually had a base 20 number system because they used both their fingers and their toes. And the word digit actually comes from the Latin word digitus, meaning finger. So the question then comes down to, what base should we use in computers? Now, this is not as clear-cut an answer as it might seem. Binary is an obvious choice because we can represent every state of the computer discretely. And for every additional transistor that we use to represent a number, we've effectively given ourselves another position to work with. However, we can actually use transistors to represent decimals. The problem is that we need more of them to do it. Let's take a look at an example here to see why. If we wanted to store the number 202 in binary, we would do so like this, as 11001010. Now, don't worry about the conversion just yet. We're going to do that in just a couple of slides. For right now, I just want to show you the difference between the representing 202 in binary form versus 202 as decimal encoded in binary. Remember, at the end of the day, the computer still only has transistors to represent things. So in order for us to encode a decimal number in those transistors, we have to represent every digit with a set of transistors. Now, in order to represent one single decimal digit, I need 4 transistors. The reason for that will be clear in a few moments, but effectively our largest decimal digit is a 9. And because our largest decimal digit is a 9, that means that the number 9 in binary is represented as 1001. That means that I need 4 transistors to represent a 9 and also an 8. Because of that, I need a grand total of 12 transistors to represent 3 decimal positions. So to store the number 202 in decimal requires more switches than it does in binary. Now, this is still actually done, and there's really good reasons why. It's just not the common way to do it. A little bit later, we're also going to talk about an encoding scheme called binary coded decimal, which is effectively what we've just done, encoding a decimal digit into binary. This is still done, and it's done usually for precision purposes. As you'll see, there can be a loss of precision when you're using fractional numbers and converting from one base to another. Encoding decimal numbers in binary avoids this loss of precision. Now we're going to learn how to actually convert between two bases. We're going to start with decimal, and then we're going to learn how to convert it to binary. First, let's take a quick look at what we already know about decimal, just so that when we apply this to binary, it helps it make a little bit more sense. Back in grade school, you learned about the ones, the tens, the hundreds place, and eventually, of course, the thousands and 10,000s, 100,000s, millions, etc. Well, what those places actually represent is your base to an increasing power for every place. Now, you might remember that the zero power rule in mathematics says that anything to the power of 0 is 1. So when we say 10 to the power of 0, what we're actually saying here is that that is represented by a 1. The times n is that we're going to take whatever that weight is and multiply it by the value that's stored there. So in this case, a 3. So in the ones place in decimal, we're saying that this is 1 times 3 is actually a value of 3. If we bring it up to the tens place, 10 to the power of 1 is 10, so 10 times 9 is a value of 90. And if we combine those two things, we get 93. And we can see that down here. You can take 1 times 100. 9 times 10 plus 3 times 1, and we get the same 193. This should be very intuitive because, of course, we just look at this number and know this, right? We might not have broke it down this way, but this is, in fact, what we are doing. What we've learned here is that we're representing each place with what's known as a grouping. So the grouping is the weight, or the base to the power of the place, times the value represented. Now that we've broken this down, let's see how we can apply it to binary. Here we have the same number, 111, represented in base 10, and 111 represented in base 2. When we apply the groupings above the places to see how we explain the values, we can tell that the only differences is the actual base used to the power of the place. So in decimal, we have 10 to the 0, 10 to the 1, and 10 to the 2. And then in binary, we have 2 to the 0, 2 to the 1, and 2 to the 2. Both times we multiply this by the value to figure out the actual value for that place. In decimal, we know that this means that we're going to have 1 times 100, 1 times 10, and 1 times 1. So we're going to have 110 and 1, and added together they equal 111. In binary now, we're going to have 2 to the second power, which is 4, times 1, which is 4. We're going to have 2 to the first power, which is 2, times 1, which is 2, and 2 to the 0 power, which the 0 power rule tells us is 1 times 1, which is 1. We add those together, so we have 4 plus 2 plus 1, and we get 7. To make things a little bit simpler, now that we know how this works, we can look at the base to the power of the place as a weight, and the results of that we can just now use to multiply the value by and achieve the result. Let's look at one more example. This time we're going to change one of the values to a 0 just to have a contrast. So here we have a 1, 0, and 1 in binary. Using what we just learned, we're just going to replace the range at the top with the weight. So we have a weight of 1, 2, and 4 in each place, and we know that we multiply the value at each place by the weight. So we have 4 times 1 is 4, plus 2 times 0 is 0, plus 1 times 1 is 1. So 4 plus 0 plus 1 equals 5. Congratulations, you now know how to convert from binary to decimal. Let's see this with a larger example. So we know that if we take our weights, remember our weights are just our base to the power represented by the position of the place starting with 0. So 2 to the 0 becomes 1, 2 to the 1 becomes 2, 2 to the 2 becomes 4, etc. Now we know that we take these weights and we multiply them by the value. So we're going to have 1 times 32 is 32, 0 times 16 is 0, 8 times 1 is 8, 0 times 4 is 0, 1 times 2 is 2, and 0 times 1 is 0. We add up 32, 8, and 2, and we get my favorite number, 42. So now that we know how to convert from a binary number to a decimal number, let's take a look at how to do the opposite. Since we multiply the value of a binary digit by their weight in order to determine the decimal equivalent, we can actually do the reverse by dividing a decimal number by the weight to determine its binary value. Let's look at the rules a little bit more formally. First, we're going to start by dividing our decimal number by the largest binary weight that is not bigger than the number. Then we're going to take the remainder and find the next largest weight that can be divided into it. And we're going to repeat until there's no remainder left. Let's start with the example 392 in base 10, and we're going to convert this to binary. I purposely have started us with a weight that's too large, being 512. The first weight that can be used is 256. So if we have 392 divided by 256, that would give us a 1 and a remainder of 136. We can't use the 512 because we can't divide 512 into 392, at least not with a whole number result. So now we're going to take that remainder and we're going to find the next weight that we can divide into it. 136 does happen to be divisible by the next weight, 128. That also results in a 1 with a remainder of 8. Now the interesting part here is that 8 is not divisible into 64, 32, or 16. It isn't until we get to weight 8 that we can actually divide it. When we do, we don't have a remainder. Now our final output is going to look like this: 1, 1, 0, 0, 0, each one of those zeros representing weights that we were not able to divide our remainder into. Another 1, which is in the 8th place, which is where we were able to divide it with a non-remainder result, and then zeros for all the weights that followed. What's important here is that you have to remember the weights that result in zeros. Let's break this down another way to see that better. So here we're going to represent the same thing a little bit more concrete. We start with the same 392 divided by 256. We get 1 with a remainder of 136. We bring this remainder down to the next weight and we try to divide it by the next weight, which is 128. We can do that with a 1 remainder 8. We now only have an 8 as a remainder. The 8 comes down and we try to divide it into 64. And we try to divide 64 into it, which obviously does not work. So we get a 0 as a whole number and a remainder of 8. This 8 keeps coming down. We cannot divide 32 into 8 and result in a whole number, so we have a 0 and we keep the remainder coming. We cannot divide a 16 into the 8, so the pattern continues. And now here we can divide an 8 into an 8 with a result of 1 remainder 0. The remainder still comes down, so the 0 still comes down here, and we cannot divide a 4 into 0, nor can we divide a 2 into 0, and lastly, we cannot divide a 1 into 0 and have a whole result. So we end up with a 0, 0, 0. What you're looking at here is your answer: 1, 1, 0, 0, 0, 1, 0, 0, 0. It's worth noting at this point, before we go into other bases like octal and hex, that once we determine the weights for each of our positions, those are the important things we need to know to either multiply or divide by. This chart gives us a cheat sheet that we can use to determine which weight goes at which position. So in base 2, you can see that it's powers of 2, so I have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, so 1, 2, 4, 8, 16, 32, 64, etc. Base 8, of course, now goes up by powers of 8. So I have 1, 8, 64, 512, 4096. Base 10 should look very familiar. So 1, 10, 100, 1000, 10,000. And base 16, we're going up by powers of, you guessed it, 16. So 1, 16, 256, 4096, 65,536. These numbers get quite large quite fast. Let's see now how to go from octal to decimal, knowing what we know and using the correct weights. Let's take the octal number 624 in base 8 and we want to convert it to base 10. What we do here is, just like we did in binary, we use a place that has the radix, or the base, to the power of 0, 1, 2, increasing as we go up in places. So 8 to the power of 0 is a 1. Our value in the ones place is a 4, so 4 times 1 is 4. 8 to the power of 1 is an 8. We have a 2 in the 8th place, so 2 times 8 is 16. And then 8 to the power of 2 is 64, and we have a 6 in the 64 place. So we now have 384. 384 plus 16 plus 4 equals 404 in decimal. Let's now see how to do the reverse and go from decimal to octal. So if we start with 392 in base 10 and we want to go to base 8, we would have to examine our weights and see once again what is the largest weight that we can use to divide into the number without being larger than. The answer here is 64, since 512 is larger than the number. I can divide 64 into 392 and get an answer of 6 with a remainder of 8. The remainder then comes down and is divided by the next base. So 8 divided into 8 gives me a 1 remainder 0. Now remember, this 0 has to come down and be divided by the last weight, which is 1. But 1 divided into 0 is still a 0. So my answer is 610 in base 8. Let's look at hex. Remember, for hexadecimal characters, you may see A, B, C, D, E, or F representing the numbers 10 through 15, because in any given place we can represent any digit from a 0 to an F, which is a 15. Here we have our places as 16 to the 0, 16 to the 1, 16 to the 2, and we can see the weights right under them. 1/16th place, 256th place, and 4096th place. So we know that we're going to take our values here and we're going to multiply them by the weights to achieve the decimal equivalent for that place. So here I have a value of 4 and a weight of 1, which gives me a 4. I have a value of 0 and a weight of 16, which gives me a 0. A value of 7 and a weight of 256, which gives me 1,792, and a value of 6 and a weight of 4,096, which gives me a value of 24,576. When you add all three of these up, you get 26,372, which is the decimal equivalent of 6704 in hex. Now we'll do the same thing going the other way. We have the number 463 in base 10, and we want to convert it to base 16 or hexadecimal. Remember, we need the weight that is the largest that we can divide into the number without being larger than the number. The weight 4096 is too big, so we're going to start with the next weight, which is 256. This is a really good time, by the way, to have that weight sheet available to you, so that if you're not familiar with the weights for each place, you can look on the chart to find the best one. So 256 divided into 454 is 1 with a remainder of 198. Remember, we take the 198 and we bring it down and we divide it by the next weight, which is 16. We can do that 12 times. Now remember, in hex, 12 is represented by a C. So if you write a 12 here in decimal, just remember that when you give a final answer, you're going to want to record it as a single digit hexadecimal answer, which in this case would be a C. The remainder is 6, which we're going to bring down and divide by our final weight, which is 1. That means that we end up with a value of 6, remainder 0. So our answer is 1C6. So that is our hexadecimal equivalent to the decimal number 463. There's one more way that we can convert to and from decimal. This is referred to as the alternative method. Now, it's important to note here that there's no fundamental difference between the two methods. That means that you have to apply one in a certain circumstance versus another. This is simply a matter of choice. If you're comfortable with the first version, you don't have to mix and match and use this, but it's worth exploring this because some people find using weights easier and some people find using bases easier. So that brings us to what is the difference? Well, we stick with the multiply to and divide away. Remember, where multiply to decimal, divide away from decimal rule applies. The main difference here is that instead of doing it by the weight, we're going to do it by the base. There's also some differences in how you order the information. So the least and most significant digits actually get switched. So let's take a look at how to go from any other base to decimal using this alternative method. What we're going to do is start from the most significant digit and multiply by the base. Then we're going to add in the next digit to the right. We're going to repeat this pattern until we've added in the least significant bit. So since we're doing binary to begin with, let's look at 1001. We're going to convert this to decimal. So we take the first digit, which is a 1, and we multiply it by the base, which is 2. That gives us a result of 2. We then add in the next digit. Note that I colored these in blue to match. So 2 plus 0 is 2. I now multiply by the base again, and I get 4. I bring down the next digit, which is another 0. I add that to the 4. I multiply by the base again to get 8, and then I bring in the last digit, which is 1. 8 plus 1 equals 9. Now this works. We can see that 1001 equals 9. I'd like to point out that at this point, hopefully with binary, you can start getting comfortable looking at a binary number and kind of picturing the weights in your head above it. So for example, we know that this would be weight 1, 2, 4, and 8. So just by visioning that, I can look at this quickly and know that I have 1 8 and 1 1, and therefore I have a 9. You want to get really good with the first 8 bits and being able to just look at them and convert. Practice it until you can. Let's look at octal and do the same thing. So if I have 7263 in octal and I want to convert it to decimal, I take the first value of the place, which is 7, and I multiply it by the base, which is 8, resulting in 56. I then take the next digit's value and add it in, which is 2. I now have 58, and I multiply by the base again. I end up with 464. Adding in the third digit's value of 6, I end up with 470. I multiply that by the base to get 3,760, and then I add in my final place's value, which is a 3. My end result is 3,763 and base 10. Last for this, let's look at hex. I'm going to start with 2AC3. Remember, an A is 10 and a C is 12. So I take my 2 and I multiply it by 16, which is the base, getting 32. And then I add in my second most significant digit's value of 10, and I end up with 42. I now multiply by the base again, getting 672, adding in the next digit's value of 12, which remember is our C, and now I have 684. Multiplying that by the base of 16, I end up with 10,944, and then I add in my last value of 3 for a grand total of 10,947 base 10. Now that we've seen the alternative version of going from another base to decimal, let's look at the alternative version of going from decimal to another base. Just like before, we're going to divide away. Remember, we're going away from decimal, so we want to divide away. And like our other alternative approach, we're going to this time use the base instead of the weight as we did in the original approach. What's important here is that now the quotient is what continues on, and the remainder becomes part of the value of that position in the new base. You'll also see that the most and least significant bits are flipped. So let's look at this with the number 42. We're going to take the decimal number 42 and convert it to base 2 using the alternative decimal to binary approach. So we start with 42, and instead of dividing by the weight like we did in the standard approach, we're going to divide by the base. So 42 divided by 2 is 21, and there happens to be no remainder there, so the remainder is 0. Now what's important is that this is actually the least significant bit in the answer. We take our quotient and we bring that down this time instead of the remainder, and we have 21 divided by 2, which gives us 10 remainder 1. Now the remainder 1 here is part of the answer, but the 10 now moves down to the next part. So 10 again is divided by the base, and we end up with 5 remainder 0. The 5 comes down and we divide it by the base again for 2 remainder 1. The 2 comes down, we divide it by the base for 1 remainder 0. The 1 comes down, and we divide it by the base for 0 remainder 1. Now note that the bottom is the most significant digit again, so our answer is 101010. Let's also look at going from decimal now to octal. So same rules, but different base. We start with the number in decimal, 392, and we divide it by the base we want to go to, which is 8. The result is 49 remainder 0. We leave the remainder 0, that's part of the answer. We take the 49 down and we divide that by the base again. We end up with 6 remainder 1. Again, the remainder remains, and then we take the 6 and we divide it by 8, and we end up with 0 remainder 6. Remembering that at the bottom we have our most significant bit, or digit in this case, because it's not binary, I apologize for that. The answer is 610 in octal. Using the alternative method to go from decimal to hexadecimal, we'll start with the number 456 in decimal. We divide it by the base, which is 16. We end up with 28 and a remainder of 6. We then take our 28 and divide it by the base again, and we get a 1 remainder of C, or 12 in decimal. And then we take our 1 and we divide it by 16 to have 0 and a remainder of 1. Remember that the bottom represents the most significant digit, and we end up with 1C6. Congratulations on learning how to use different number systems and convert between any of them, but specifically binary, octal, hexadecimal, and decimal. There was a lot of resources that went into creating this presentation, and please do check those out here if you want to learn more. Thank you for watching. A video will be following this one detailing how to do basic mathematics in different bases, so if you want to see that, please check that out here. Please do like and subscribe, it helps a lot, and thank you for watching The Coding Coach.